Hello, problem solvers. We are going to work on lesson 15 now, the ice sheet, which is on sums and products. And you'll notice when you look at this sheet, the ice sheet, that there's a fifth problem that says for fun, and it says, I do not know the solution. That was a contest problem that one of my, the guy that used to teach this class, Dr. DeLong, his son had that on a math competition, and neither of them know the answer. And so I still don't know the answer, but if you want to try it, feel free. But I do know the answers to the first four, so let's try these. So it says, find the formula for a product of the terms of a geometric sequence. So normally what you might say, hey, I already know that formula. You do for a sum of a geometric sequence, right? The a over 1 minus r, or the finite sum formula. This is different. This is a product. So if you have a, and then you have ar, and then you have ar squared, and then you have ar cubed, well, and the last term is ar to the n, so we're going to say the product of n of them. I don't know if it says that explicitly. Yeah, it says the last one is ar to the n. Okay, well, how many a's do you have? Remember that you have a to the r to the 0 as well, right? So 0 and then 1. So you have n plus 1 a's, that's the easy part. How many r's do you have? Well, 1 plus 2 plus 3 plus, and the last one's n. But you guys already know a formula for this. The sum of the first n integers is n times n plus 1 over 2. We proved that with induction a long time ago, and then we did the proof without words, right? So that's all you need for the first one. That is a nice final formula for the product of a geometric sequence. Okay, the next one says prove this identity. And let me write down that. Oh, I gotta hit myself. That was number 3. Okay, so number 2 says find the sum. And I'm gonna write out some stuff. Root 1 plus root 2. Now they could have written 1. They're trying to show you the pattern. Root 2 plus root 3. And then root 3 plus root 4. And then they want to stop at n, so there's n terms, and then this one here, but it goes from 1 to n. Okay. It's easy to look at this and say, hey, I don't know what to do, except the simplest thing to do would be to rationalize the denominator, because I don't know what else to do with square roots. I don't like this. I'm looking at that and I'm confused. So let's rationalize that. So let's do it in general. So let's look at that last term, but I don't want to use n. I don't want to confuse myself. Think about a general term as, so if this is like a0, or I guess in this case we're starting with n equals 1. So if that's a1 plus a2 plus a3, and the last one is an. Usually if we're already using n, then we're going to say ak is this expression. Why we use k and n, I don't know. My point is to use a different letter, just so you don't get confused. So that's just an arbitrary term. K is between 1 and n. And let's rationalize the denominator. So do subtraction here. And hope this turns out well. So I have k minus k plus 1 up top. That part's easy peasy. The bottom requires some foiling. And remember, anytime you do this, the middle terms cancel. So I'm going to skip that. I'm going to get k minus the quantity k plus 1. The bottom becomes minus 1. And so I guess I should just flip these around to get rid of that. Okay, so every term could have been written like this instead. So let's do that up top. So the first term is actually root 2 minus root 1. That's a1. And then root 3 minus root 2 is a2. And then the last term is actually root n plus 1 minus root n. And what you should notice here is that this telescopes. Those cancel. That cancels with the next one. This cancels with the previous one. And the only things that don't cancel are this very last n plus 1 term and then 1. So that's going to be your final formula. Alright, so telescoping series, very common trick. With infinite or finite series. And also, just remember, a big part of this class is going back to your old bag of tricks. Don't forget all the stuff you learned in Algebra 2 and pre-calcs. Rationalizing the denominator is still a good trick. All right, let's go to the third one here. And we want to prove an identity. They give you the answer. So you have this finite sum. K goes from 1 to n. And it's k squared plus k factorial. K squared plus 1 quantity times k factorial quantity. And they said it's n times n plus 1 quantity factorial. Make that k more clear. Okay, so I want to try to telescope again, because not really because you should see that right away, but hopefully after you do a lot of these, you'll see that telescoping is a very common trick to pair with factorials. So that's really where that idea is coming from. And also, these kind of look like factorial-ish. What would be easier would be if I had k plus 1. So this is wishful thinking. K plus 1 times k factorial. Well, that would be k plus 1 factorial, because that's how factorials work, if you don't remember that. And so I would rather have something like that. That k squared is giving me trouble, but maybe I can play with this sum. So let's go ahead and try to figure that out. So let's focus on that k squared plus 1. And let's try to make a k plus 1 inside here. Well, I have k squared doesn't help. I have the 1. So just thinking about this. I can add a k, but I'll have to subtract a k as well. Okay, so that's still the same. So if I put k factorial here, that's still the same. So this is really the right thing that I started with. This is my wishful thinking, so I'm going to bubble that because that's a separate thought. Now, let's group these. I don't know if this is helping. We'll find out. K squared minus k. That can be times k factorial. And then k plus 1. That can be k factorial. And this is k plus 1 factorial. Did that help? I don't know yet. Okay, so over here, I can pull a k out because I don't know what else to do. Okay, so now let's look at what we got. Alright guys, so when I'm at this point, I'm going to keep going. I'm going to talk through this a little bit. I'm a little stuck here. If I notice that I have two positive things that I add up, which is going to make it hard to telescope, so something's wrong. The other thing about telescoping is that you want, this is like one more than that, but this stuff doesn't really match, right? I want the same thing twice subtracted, where one looks slightly bigger, like one term bigger than the other, and these don't match up. I still feel good about this idea that I need a k factorial and a k plus 1 factorial. So I didn't do anything illegal, I just don't think it's helpful. So let's go back up. The only thing I can do is really to switch these. So I'm going to try again. And so what I'm going to do here is I'm going to do k squared plus k minus k plus 1. And just to try to do a minus sign here. So I'm going to do k squared plus k factorial. I could do a minus 1 here, but it doesn't go anywhere. I saved you guys having to watch that. So if I do a minus here, well, that would be a k minus 1 k factorial. And then I can factor a k over here to get k plus 1 factorial minus, k plus 1 and then k factorial. And then minus that other stuff. Okay, now we're going to use our trick where that's really k plus 1 factorial, and then you need to, at this point, stop and stare at it for a minute if you're not already. Okay, why does this work for telescoping? Look at this carefully. It doesn't really matter how it's laid out, other than it's the exact same expression, except everything is 1 different. K is 1 higher than k minus 1, k plus 1 is 1 higher than k, and they're subtracted. So now this should telescope. So when k is 1, so this is the general term now, and when k is 1, you get 1 times 2 factorial minus, I guess, 0 times 1 factorial, which is going to be nothing. And then when k is 2, you're going to get 2 times 3 factorial minus 1 times 2 factorial, and you can see how that's going to cancel with that. And then we're going to keep going, and then the very last term is going to be n times n plus 1 factorial minus n minus 1 times n factorial, but that should cancel with the previous term. And this extra term was 0, so the whole thing just becomes this, which is what they actually showed you at the beginning of the sheet. That was the identity you were trying to prove. That one's a doozy. The point, I went through this even though this was wrong, because I think it's worth mentioning when you're trying to make something telescope. Sometimes you'll do something that's legal but wrong. And that's worth you guys seeing me go through that. I know it's a little annoying, but don't think I'm just magically getting these right every time. All right, the last one is, I want to sum from k equals 2 to n, 1 over log k of u, and u is some number that I don't know, but I want a formula for that. They were doing log base k here, and so there's a formula that you need to know here that you may not know or may have forgotten that's related to change of base. Okay, so for a minute I'm going to just talk through the change of base formula, and maybe you forgot some stuff about this. So in general, let's not do the 1 over, let's just talk about, we'll come back to that, but let's just talk about this bottom part, log base k of u. If you want any other base, so usually it's ln, probably you learned it like this, ln of the argument over ln of the base. Ln doesn't have to be that, it can be anything. You can use any logarithm base, and you just switch it like this. This is called the change of base formula for logarithms. So if I did log base u of u over log base u of k, well, that would say that, remember this is 1 because they're the same. So it says 1 over log u of k is equal to log k of u. So those two are reciprocals. If you switch the base, in the argument, they are reciprocals, which is pretty crazy. Okay, so that means up here, a simpler way to write this, because the denominator was kind of freaking me out, I can do log base u of k. And so that's going to be k from 2 to n. Now, when you think about how to multiply this out, well, so this was just our scratch. Let's multiply this out. It's going to be log base u of 2, log base u of 3, log base u of n. And the advantage of getting rid of that denominator is now, when you think about this, this is just going to be a logarithm trick, right? Where if you are, sorry, we're adding these, aren't we? And that's why we couldn't do that before, because we were adding on the cross of the denominators, but now that we're adding straight across, the logarithm trick is that this becomes a product. So 2 times 3 times to n, and there's no 1, but 1 multiplied by 1 wouldn't do anything. So that's really just log base u of n factorial is the final formula there. So don't forget your logarithm tricks, especially when you're doing sums and products, because they let you move from one to the other. All right, so that's the end of the lesson 15 sheet.